Hey everybody, Dr. A here, and in this video we're going to be providing some background information on three-dimensional particle equilibrium. But before we get started, don't forget to hit like and subscribe and be on the lookout for other content like this. Alright, let's get started. In this video, we're going to be discussing three-dimensional particle equilibrium. So this is going to be wrapping up chapter 3 of our textbook. So this topic is a pretty nice, smooth transition from two-dimensional particle equilibrium now in 3 dimensions. So for a particle to be in equilibrium in 3 dimensions, we apply how many equations of equilibrium? So maybe pause the video and think about that. For 2D particle equilibrium, we have 2 equations of equilibrium, right? Some of the forces in the x and some of the forces in the y directions must equal 0. What about a 3-dimensional particle? Well, we still are not dealing with any kind of rotations yet. We're still just dealing with force components. But in this case, we're going to apply 3 force equilibrium equations. Okay? So the way to think about that is sum of all the force vectors equals the 0 vector, and specifically we're going to have sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and sum of the forces in the z direction equals 0. And from these 3 equations, again, these are 3 equations to solve for 3 unknown quantities, 3 unknowns, okay? Other than that, we're following very similar procedures we saw in 2 dimensions. Now, here's some other points to be aware of, okay? So, when coplanar forces are present, some calculations will simplify. Now, what do I mean by this? Well, the whole system we're dealing with may be 3-dimensional, but we may have some forces that are only present in one single plane, and we're going to see some examples of this. So while the whole system may be 3D, you may have a particular force that only has, for example, an I and a J component. Or maybe you have one force that only has an I and a K component. That would mean that that particular force is only in one plane. So we're going to make a little note of this. We're going to say this occurs when one of the forces in the system only has 1 or 2 components instead of 3. Components. So like, for example, again, I'll put a little, I'll say i.e., for example, you may have a force that has maybe F sub x I plus F sub z k, okay? Or a force that's F sub x I plus F sub y j, or a force with F sub x, F sub y j plus F sub z k. So for example, these 3 forces that I just kind of sketched in here, notice they only have 2, each of them only has 2 components, which means each of these forces would be a coplanar force, right? This force right here is in the xz plane, right? This force is in the xy plane. This force is in the yz plane. So while your whole system will be 3-dimensional, you could have a particular force that's planar, right? Or multiple forces that are coplanar within one plane. And when that happens, some of your calculations can really reduce and become simpler to deal with. So it's always best when you're dealing with 3D particle equilibrium problems, recognize the potential presence of a coplanar force, because again, that could really simplify your calculations, and you can avoid some computational headache. So in the next couple of videos, we're going to get into some examples illustrating these types of problems.